Now the last case that we're going to consider is the resonance, right? So the simplest examples is a swing. So because how does a swing work? So it is moving to the right, and then you try to push it further to the right. If it is moving to the left, you try to push it further to the left. So which means that the frequency of the driving force, which is your pushing, is the same as the frequency of the swing itself. So now let's look at the equations. Now, well, if we still have the same undamped left-hand side and the driving force in the right-hand side, but suppose now that the frequencies are the same, right? So if the frequencies are the same, it means that so here omega 0 is what, square root of k over m. Right? So then the formula that we derived in the previous part doesn't work. Then what we're going to do, we're going to go through variation of parameters one more time and see how we can use variation of parameters to derive a particular solution. Now recall that here is the formula for u1. So this is u1 in variation of parameters. Yeah, and this is the formula. It is complicated, of course, but it's not too bad because the Wronskian here is a constant, so you can just put in all the information, and then you can use Wolfram alpha to integrate it, and here is the answer. So that's u1. Then for u2, very similar. So you enter all the information that we know, g of t, w, and so on, and then you use Wolfram alpha to integrate. Well, strictly speaking, the integrals are not too challenging even without Wolfram alpha, but anyway. Right, so then putting it all together leads to a long and scary formula. So that's the particular solution. So a challenge for you, and this is actually a very meaningful question, and I suggest that all of you at least try. You don't have to report it to me, but you should try. So the interesting thing is that that's a formula for the particular solution, and it looks, well, big. But as a matter of fact, if you simplify, then this term is going to be gone, and this term is going to be gone, and only this part remains. So which means that the general solution of the differential equation is a combination of three terms. This is the general solution of the homogeneous differential equation, so it's just oscillation. But that's this is the resonance part. So this part is what causes the resonance. Right? So why does it cause the resonance? Because what you have here is a linear function times a trigonometric function. And then you can imagine that if you have a linear function times a trigonometric function, then if, say, this is our linear function, this is minus the linear function, then if you multiply them together, then you're going to have oscillations of increasing amplitude. And this is what actually happens. So, for example, with the initial condition, when one of them is displaced, the other one is just 0. Actually, even the displacement does not need to be present here, so you can just do it without the initial displacement. It's still going to cause these increasing oscillations. Right, and then what you see is that these oscillations, they happen between two linear functions, and as t approaches infinity, the amplitude is increasing. Alright, so here is the particular example that that you see here, and I suggest that you click this link to play with the graphs around to have a better understanding of what the plot is going to look like. Well, and finally, of course, logically, there are free oscillations versus driven oscillations. So free oscillations may be damped or undamped. So driven oscillations may be damped or undamped. There could be resonance or no resonance. So, and the last case that we have not covered is damped driven oscillations. So there may be a resonance or there may not be a resonance. So if there is no resonance, then basically what's going to happen is that because of damping, the natural oscillations of the spring mass system are going to eventually disappear, and the system is going to follow the driving force. With resonance, we are going to see kind of a similar effect as with undamped oscillations, only now, of course, damping is not going to allow the amplitude of oscillations to increase to infinity, so eventually the amplitude is going to stabilize. So, and then you can click here to take the last quiz, and it's a very long quiz, so you'll probably have to spend a lot of time on it.